cellular automata, and emergent order. Simple rules, complex patterns. So let's make the rules explicit and press run. Take a grid of squares, each one either alive or dead. Now give it 4 lines of law. A live cell with fewer than 2 live neighbors dies. With 2 or 3, it survives. With more than 3, it dies. A dead cell with exactly 3 neighbors becomes alive. That's Conway's game of life. No randomness, no hidden variables, just local checks every tick. Stakes first. If these toy rules can grow order, then code-like isn't just a metaphor. It's a lesson about how complexity hides in locality. Life's grid spawns gliders, little 5-cell arrows that slide diagonally, blinking as they go. Patterns collide, fuse, and spit out new movers. Engineers watched and realized, with the right scaffolding, these pieces compute. People built logic gates, counters, even universal Turing machines inside life's universe. From 4 lines, you get a world that can emulate any algorithm. That's not poetry. It's proof that trivial update rules can host open-ended dynamics. Action on a screen. Start with noise, a sprinkle of live cells. The chaos doesn't stay chaotic. Islands emerge. Some freeze into still lives, some orbit in small loops. Gliders crawl into the emptiness, map edges, then crash. Add a glider gun, and it fires a steady stream forever. Classify what you see, and you bump into a taxonomy. Class 1 rules settle into uniformity. Class 2 into cycles. Class 3 devolve into randomness, and Class 4 live at the edge. Pockets of structure riding a sea of change. That edge of chaos behavior is a sweet spot. It transports information without freezing. It adapts without drowning in noise. Meanwhile, something humbler than life mimics plants better. L systems don't evolve on grids, they rewrite strings. Start with a symbol, apply production rules, replace A with AB, B with A, and iterate. Read the final string as drawing commands, and a fern appears. Add a slight randomness to angles, and the fern stops looking like a stamp and starts looking like the one in your yard. Branch after branch, a grammer writes a canopy. With a few lines of text, you get trunks, twigs, and veins that feel grown because the process is growth. Replace, extend, bifurcate. Impact lands in design. A programmer once grew a forest for a game with maybe 10 lines of L-system grammar. Artists get infinite variation for almost no memory cost. That's compression, a small description unfolding into a huge scene. Antenna engineers carve fractal edges, Koch curves, Sierpinski gaskets, into metal and get broadband performance, because self-similar perimeters interact with many wavelengths at once. Chip routers borrow space-filling curves to snake signals in tight quarters, reducing crosstalk. It's the same story. Local rule, global payoff, minimal overhead. But there's a caution tucked in here. It's easy to mistake resemblance for mechanism. Just because an L system draws a convincing maple doesn't mean a maple uses a string rewrite engine. Biology lives in chemistry, growth hormones, and mechanical stress. The value of these models is twofold. They prove sufficiency. You can get plant-like branching from simple grammars, and they reveal constraints, branching angles and ratios that keep showing up even when you change the rules a bit. Back to life for a beat. There's a reason Class 4 fascinates. Systems poised between order and chaos can compute, store, and transmit information. Tip the rules toward order and perturbations die. Tip them toward chaos and signals blur. Near the edge, gliders carry bits, collisions implement logic, and stable motifs serve as memory. That framing bleeds into thinking about brains and ecosystems. Maybe adaptability requires living near a transition. It's a tempting bridge, but the test, as always, is predictive power. Does the edge of chaos idea forecast measurable exponents, response curves, or failure statistics in real networks? Meanwhile, parallel action in cellular automata beyond life shows different flavors of emergence. Rule 110, a one-dimensional update rule, also supports universal computation. Wolfram's explorations cataloged how small rule tables produce stripes, triangles, and pockets of surprise. Some rules produce pseudo-randomness with spectral fingerprints, useful for texture synthesis and testing. Others self-organize into crystalline domains with moving defects. The lesson repeats. Detail isn't needed for richness. Locality is enough. Stakes again. If code can paint nature's vibe, are we looking at nature's code? Here's the line to hold. These rule sets demonstrate that finite descriptions can grow vast complexity, and that compression is real. They also show that emergent order can be sensitive, robust, or brittle, depending on where rules sit in parameter space. That's valuable because it guides how we search for models. Look for short descriptions that match many scales. Expect universal. Behavior, when systems forget their micro details. But the bridge to the universe runs code needs a test. It's one thing to say life can host Turing machines. It's another to claim space-time updates on a lattice. We can ask for signatures, discretization artifacts, bounded correlations, compressibility thresholds. Until those show up, cellular automata are inspiration and laboratory, not proof. Still, notice the economy. A handful of rules gives you gliders, guns, and computers. A tiny grammar draws a forest. A short function plots a coastline lookalike. That economy is why compression matters. The shortest description that reproduces the data, Kolmogorov's idea, measures structure. Fractals pass that test because finite rules generate infinite detail. Up next, we'll take that compression lens and point it at the universe itself to see whether nature prefers short code or whether some patterns are irreducibly long. Compression test, Kolmogorov complexity and nature's shortcuts. Simple rules spun lifelike order on a screen. Now ask the sharper question, how short is the shortest description that reproduces what we see? That's Kolmogorov complexity, the length of the smallest program that outputs your data. If a pattern compresses well, it has structure. If it refuses, it's random, or at least beyond the reach of your current compressor. Science in that sense is compression. Boil thousands of data points into a law that predicts them. Newton zipped orbits into 3 lines. Maxwell zipped electricity and magnetism into 4. Good laws are small files that unpack into huge worlds. Fractals are compression machines. Take the Mandelbrot set. A single iteration rule, z squared plus c, draws a boundary with endless intricacy. You don't store every wiggle, you store the rule. L systems do the same for ferns. Even the coastline paradox turns into compression when you capture the scaling law instead of listing every rock. This is why a tiny shader program can render a cathedral of detail at 60 frames per second. The code is short, the output is vast. Stakes first. A compressible universe is a universe you can navigate. You don't memorize weather, you track fronts and pressure laws. You don't memorize every heartbeat. You learn how signals propagate in tissue. If reality were irreducibly long everywhere, models would fail. Engineering would be guesswork, and prediction would be luck. The fact that we get traction across physics, biology, and geology means there's structure to catch, patterns that let us throw away most of the data and keep what matters. Action in practice. Scientists test compressibility without ever touching Turing machines. They fit models and compare description lengths. How many parameters, how much residual noise. The minimum description length principle formalizes the trade. Shorter models win unless they leave too much unexplained. It's a check against overfitting and a pressure toward mechanisms that generalize. In many systems with fractal vibes, rivers, bronchial trees, critical clusters, description length shrinks dramatically when you switch from raw maps to scaling exponents and universality classes. You drop gigabytes, you keep a slope. Meanwhile, randomness stalks the edges. True Kolmogorov complexity is uncomputable. You can't guarantee that your compressor is optimal. Pseudo-randomness complicates things further. A short program can generate a sequence that passes many statistical tests for randomness, fooling compressors and humans alike. Cryptographers rely on that gap. Nature uses something like it too. Turbulence, with its 1F-like spectra and cascades, looks random, but follows conservation laws and energy flows. You compress the cascade model, not the exact eddy. Impact lands in data-hungry fields. In cosmology, the cosmic microwave background, the afterglow of the Big Bang, compresses surprisingly well into a small set of parameters. Overall amplitude, spectral index, a handful of ratios. On the sky, you see modeled noise, but its statistics match a near-scale invariant spectrum as inflationary models predict. That's a short file generating a universe of spots. Yet anomalies sneak in. A cold patch, hemispheric asymmetry hints. Are those true features or flukes that evaporate under better compression? Teams build careful null tests because a single unjustified parameter can fake meaning. Back on Earth, compression guides medicine. Instead of tracking every pixel in a lung scan, radiologists compute fractal dimension and texture spectra. Those compressed features outperform raw intensity lists for predicting decline in diseases like COPD. In neuroscience, sparse coding models describe how the brain might compress sensory input. Few active neurons representing multi-scale edges and textures, mirroring fractal statistics in natural scenes. AI borrows the trick. Multi-scale features and skip connections compress images into usable representations, then decompress to reconstruct with high. But there's a limit you can't sweet talk. Some structures are algorithmically irreducible. You can simulate them, but you can't shortcut to the answer without running the process. Cellular automata like Rule 110 demonstrate this. Predicting a distant state requires stepping through, not leaping over. In physics, complexity growth plays a similar role. Chaotic systems hide future states behind exponential sensitivity. Weather beyond a horizon is irreducibly costly to compress. The lesson isn't defeat. It's a map of where compression pays and where runtime dominates. What nobody knew early on was how informative compression could be as a hypothesis test for code-like reality. If the universe is running finite rules, we should expect broad swaths of phenomena to be highly compressible by short descriptions with predictable cutoffs where finite resources intrude. We do see that in many domains, scaling laws, conservation principles, universal exponents, but we also see stubborn leftovers, algorithmically long exceptions, noise that resists all current summaries, and complexity that only yields to step-by-step simulation. Caveats matter. Apparent compressibility can be overfitting in disguise. Power laws inferred over a single decade can collapse when better sensors extend the range. Log-normal mixtures can masquerade as scaling. The cure is harsh bookkeeping, cross-validation, out-of-sample tests, and penalties for extra knobs. Beauty earns its keep only when the shorter file actually predicts new data. So where does this leave the universe as code intuition? Compression proves that short descriptions can generate deep worlds. It doesn't prove that space-time is a program. Still, if nature favors low description length under constraints, energy, time, material, that's a unifying thread. Fractals are one way those savings show up. Finite rules, repeated operations, broad coverage. To really judge the code metaphor, though, we have to zoom to the largest canvas we have and ask whether the cosmos itself looks compressed, where it holds, and where it stops. Cosmic scaffolds, galaxies, filaments, and near fractals. Zoom out to the largest map we've built, the three-dimensional atlas of galaxies. Dots that are entire islands of stars don't scatter evenly. They knit into a web, bright knots linked by tendrils with vast dark voids between. Astronomers call it the cosmic web. Two galaxies close together are more likely to have a third nearby. Pull farther apart and that preference fades. Quantify it with the two-point correlation function and you get a scaling law. A power-like drop over tens of megaparsecs. It's the same feel we've seen before, clustering across scales, until suddenly it relaxes. Stakes first. If the universe were fractal forever, structure would never give way to uniformity. Gravity would clump without end, and cosmological averages would wobble with every new survey. But the stakes of measurement flip that. We need the universe to be statistically homogeneous at large scales for our simplest cosmology to work, for background radiation to be interpretable, for expansion to be a smooth concept. So the question becomes sharp. How far does the scaling law run and where does it stop? Action in the data room. In the 198s and 90s, redshift surveys like CFA started sketching slices of the sky. Wedges showed walls, filaments, and bustling nodes like the Coma cluster. With SDSS and later DSI, the sketches became portraits. Millions of galaxies traced strands, hundreds of millions of light years long. The correlation function fell roughly like a power over small to intermediate separations. Then a new bump appeared near 150 megaparsecs. The baryon acoustic oscillation scale, a fossil sound wave from the early universe. Beyond a few hundred megaparsecs, the curve flattened. Homogeneity asserted itself. The web looked fractal up to a cutoff. Beyond it, the average smoothed. Meanwhile, simulations were playing catch and then leapfrog. Feed dark matter particles, simple rules, gravity, expansion, initial noise seeded by early universe physics, and step time forward. Clumps form, merge, and draw in filaments. Voids evacuate. No one draws a filament by hand. It falls out of particles following inverse square law attraction in an expanding background. Zoom a simulation box and the view rhymes with surveys. Halos at the nodes, sheets flowing into threads, threads into knots. The near-fractal field is emergent, not mandated. Impact lands in cosmology's core. The fact that structure looks scale-free up to a scale, then washes out, lets us fit a small set of parameters. Matter density, dark energy fraction, initial fluctuation tilt, to huge amounts of data. The BAO bump becomes a standard ruler to measure cosmic expansion. Lensing maps that trace mass through warped light reveal the same scaffold without caring if matter glows. Consilience, different measurements agreeing, tightens the claim. The universe is clumpy like a near fractal at small scales and smooth enough at large scales to keep the big picture math honest. Now a human moment. A mapper sits through a night of D's-eye exposures. Each spectrum nails a galaxy's redshift. As the pipeline updates, a new slice appears. A pale fog of points then. As algorithms subtract errors and sharpen positions, a web pops out. She's seen this pattern in press releases, but when it resolves on her screen from raw photons, she forgets to sip the coffee that's gone cold. The tendrils aren't art, they're places. Billions of suns, braided by gravity, whispering an old rule. But there was one problem that wouldn't die. A camp of fractal universe. Advocates argued that homogeneity never truly arrives, that each new survey only pushes the cutoff farther. The counter is brutal bookkeeping. Homogeneity is statistical. Count galaxies in bigger and bigger spheres and watch the variance fall. It does. The rate matches expectations from LevZDM, our standard model with dark energy and cold dark matter. The web keeps its texture, but the averages stabilize. The power law slope of small-scale clustering gives way to a plateau. Meanwhile, substructure complicates the story in useful ways. Halos that host galaxies aren't smooth balls. They're packed with subhalos, smaller clumps, down to the resolution limit. That hierarchy of clumps within clumps is a hallmark of cold, dark matter. Strong lensing tests it. Background quasars split into multiple images with small anomalies that betray invisible satellites. Count those anomalies, and you probe the hierarchy's slope. Again, near fractal within a window. Again, a cutoff where particle physics and feedback heat erase small stuff. Impact for observers and modelers is concrete. Treat the web as exactly fractal, and you'll overpredict fluctuations in the cosmic microwave background on large angular scales. Treat it as too smooth, and you'll underpredict galaxy-galaxy lensing strength. The sweet spot, scale-free clustering up to tens of megaparsecs, a BAO imprint, homogeneity beyond a few hundred, anchor survey design, error budgets, and the hunt for new physics. Deviations from this scaffold, if real, would signal something deep. Warm, dark matter, smearing small scales, exotic interactions, or early universe fingerprints. What nobody knew at first glance is how forgiving the web's rules are. Change baryonic physics, star formation, feedback winds, and you sculpt galaxy properties while the dark scaffold barely flinches. The backbone is written by gravity and initial conditions. The luminous paint is local. That separation is a gift. It means we can test gravity's large-scale script, even as we argue about how galaxies quench. So, does the web prove code? It proves that simple, local laws, gravity, expansion, Gaussian initial noise with a tilt, compress into a short description that unfolds into a multi-scale scaffold. It also proves restraint. The universe isn't an infinite fractal. It's a near fractal with a horizon of sameness. That mix, a long run of scaling and a hard stop, isn't a glitch. It's the signature of rules under constraints, the same tune we've heard in rivers and lungs, now played on a cosmic stage. Efficiency under constraints, why fractals win. While that web glows on the screen, pull the camera back to the rule underneath it. Move the most stuff to the most places with the least cost. That's the quiet pressure shaping so much of what we've seen. Transport wants reach. Budgets want restraint. Fractals win because they do both. Start with the simplest framing. Suppose you need to deliver something. Air, blood, water, electrons, data. From one source to a huge, spread out set of targets. You could run a separate pipe to each target, but cost explodes with distance and count. You could lay a single broad channel, but distant corners starve. Branching splits the difference. Big trunks carry bulk cheaply. Finer branches spread coverage without hauling unnecessary diameter everywhere. The geometry is a compromise machine. Stakes first. Every extra millimeter of copper on a chip is heat and latency. Every extra centimeter of artery is pressure lost, heart work burned. Cities string power and fiber where people live. The layout sets whose lights flicker first in a storm. The wrong geometry taxes energy budgets every second. The right one saves that tax across a lifetime.